Buzz, the stage is yours. Seems like we have some small problems with audio. Just give me a second so we can see what's going on. Can you say something? Okay, I think it might be on our side. It was working just seconds ago.
And now you can hear me. Great.
Yes, now we can hear you.
So, sorry all, I'm Bas. I'm mostly working on the RedV Vulkan driver for AMD devices. And today I'm going to talk about trace-based profiling on AMD GPUs. And we commonly use profiling to figure out what the least meaningful thing to optimize is and where there are any optimization opportunities. In my GL days, it was pretty common to record something with APA trace, and then on replay, we measured things like timestamps and GPU performance counters. And we typically did that per draw call. And the way that happened with API trace is you do kind of barrier sample, draw sample again, and barrier, and then take the difference between the two samples. However, that has a big issue with interdraw effects because everything is so isolated. And these days, GPUs are kind of like a pipeline with all kinds of shared resources. So there's a lot going on actually that you can't see. Of course, your first thing to do would be remove the barriers, but that has its own little problems. Like if you look at the left, like the typical way to do this is to sample at the top and the bottom of the pipeline, but otherwise just run in parallel. And then if we look at the right side, I just put some profile information there, like draw calls and then how long they took using that approach. And if we take like the fifth call from the bottom, like it takes 361 time units. But the question is like, is that slow? Is that fast? But it's waiting on the previous draw call to finish, and you really don't know. And it's really hard to figure out like what's the real expensive draw call among all of these, or maybe they're all expensive. And for that on AMD GPUs, we have something called thread traces. And the idea is that we can have the GPU dump to a buffer like all kinds of things. Like when a shader subgroup starts or stops, when a draw starts or stops, driver annotations, command buffer register writes, or other events like cache invalidations or barriers. And we, over time, have integrated this with the RedV driver. Like you can start an application and set an environment variable to a non-existing file. And then when you create the file, it deletes it again and traces the next frame and will give you a nice buffer on the TMP directory. And then we're going to visualize that. For that visualization, I will use an existing tool called the Radiant GPU Profiler made by AMD. Not to particularly tell you how nice of tool it is, but to give you some ideas of like what kinds of interdraw effects are interesting to look at and can help you in your optimizations. And the big view from such a buffer is the Wavefront subgroup view. So from left to right, you really have a timeline of your entire frame. And at the top, we look at the shader occupancy, like how many shaders are active in your shader units. 100% is good, 0% is bad, and in the middle is non-ideal, but it's not completely perfect because with 100%, like it includes SMT, so typically with 50%, it's all right-ish. At the bottom, we have all kinds of events. So all the light blue boxes here are draw calls. The red lines around the middles are barriers. And I'll give you a zoomed in version of how that looks like. And we can see here that draws are really a bunch of things combined. Like there's 2 boxes per draw with a line between them. And that's really like your geometry pipeline versus your fragment shaders. And then you also see some draw calls without a second box where apparently all the fragments are depth called or otherwise not needing a fragment shader. And zoomed in view to the top, like you can really see like bad places, good utilization, and you can actually split this out by things like draw call. So you can actually like, if you select this in one overview, see like, is there something that takes a ton of compute resources for a long time or something like that. And when we put these together again, like on the occupancy, we clearly can see in the middle of the graph that there's some utilization problem, like it's having almost 0% occupancy. And the big hint there is I selected one of the draw calls in the lower event view, and it pops up some information on the right about the draw, and the important thing is the text in red, which says rolled. So it's about hardware context, which is really AMD's version of draw states. And yeah, if you change your state between draws, like we have to have multiple draw states in flight if we want to have multiple draws in flight. And it turns out we can have a maximum of 7 draw states in flight. And when you need another one for your next draw, but the other 7 are still busy, you're going to get a stall. So if we look at the event view and I one by one selected them and see if there was a context draw, and then put a red dot in this image for where there's a draw state change, and you see like there's like a lot of draws that change state and way more than 7. So there's a big limitation there in your throughput based on how often you can change your draw state, and not so much about being shader limited or anything like that. So this is really a limitation. And now you can figure out like how to avoid that. Like, should we spread these with more expensive draws, or should we avoid changing a state even though it's less optimal to avoid this bottleneck? So this has given you an opportunity to optimize. And another big optimization opportunity tends to be barriers. Like, for example, if you render to a render target and then want to read it from a shader, you of course have to wait till we finished rendering to the render target. The problem with that is that, like on a Vega 64, which it's kind of like you need 164K shader invocations at the same time to reach full occupancy, which is like a lot. And if you need to drain that, like that's pretty expensive. So there's basically 2 ways to help this. One, like it gives you a separate barrier field where you can go look like what are my most expensive barriers and stuff like that. And it gives you, I put some image of it below of a small set, and it gives you stuff like duration and drain time, but also like, what am I waiting for? Like, am I waiting for full GPU idle, or am I only waiting for compute shaders or vertex shaders or something like that? It tells you which caches to invalidate. Like, if you take the render target versus sampling again, like you might need to flush some caches to make that visible to the texture units. And it also tells you like layout transitions that are not visible from the application. Like, am I going to decompress an image, compress it again, or do some other thing? It also tells you, it will also show you that in the timeline we saw earlier, and it will finally tell you what triggered it. And for drivers, it's very helpful that it also tells you why it triggered the barrier. And we can actually see that in the timeline view again, like the red lines are the barriers. So if you see like your occupancy goes way down and then there's a barrier, there's a good hint that the barrier might cause it. And then you can look at like, how can we avoid that barrier? How can we make that barrier less expensive? Like, can we batch things better? Or maybe a better layout transition will involve flushing less caches or less work for, say, a decompression. And of course, as an overall profile tool, RDP will provide you with all the necessary pipeline state to figure out like, why is this decompressing or not? And that's your second optimization opportunity here that it can really visualize and that you wouldn't see by just looking at individual draw calls. A typical trace for an AA game tends to be like a half to 1 gigabyte, and if you look at the GPU, like this is less than 10% bandwidth overhead, and it's a separate hardware block that does this, so it's pretty low overhead. It's slower than timestamps without barriers, but it's faster than any of the replay tools, and typically your overall frame time will be pretty much the same as it is without the tracing. And finally, as a bonus, one of the events we can actually trace is executing instructions on a single chosen compute unit. So that's where we really can use this to look inside, say, a big compute shader to figure out like what parts of the shader are expensive. Maybe you can do something in the compiler. Maybe this is something for the app to optimize. And this is especially becoming more important as more and more games are using huge compute shaders as significant parts of their frames. Of course, not everything is perfect. Streaming performance counters are something that we can help with the occupancy problem, which is like occupancy isn't utilization. Like 50% occupancy will be if you don't need to hide latency enough to utilize all the hardware units. So ideally, you'd have something like, what's the utilization of my vector floating point ALUs? And for that, performance counters are just so much more useful. And streaming performance counters can like sample the performance counters in roughly each 100 to 200 nanoseconds. And it would be really cool if you could align that with your thread trace to figure out like, is this lack of occupancy actually causing a real performance problem here? Sadly, there's no RGP support, and RGP is not open source, so it's kind of hard to add it in to make this useful without writing something similar. So that's where we haven't quite gotten yet. And that was it. Thank you all. I hope I showed you some nice ideas for extra optimization. Are there any questions?
No, currently I didn't see any questions on IRC, so I guess that would be it then. Unless something last minute will pop up. Nope. Okay, thank you very much for your talk. That was really good to see. And see you.
See you.